Explainer. Today, we're going to dig into the science of the ground right beneath our feet. We're talking about transforming our whole idea of soil, from just plain old dirt into this complex, living foundation of, well, our entire world. So yeah, let's get our hands dirty and dive right in.
So let's just start with what seems like a simple question, but it has a surprisingly deep answer. What is soil, really? I mean, we walk on it every single day, but do we actually know what's going on down there?
First thing you gotta know, soil isn't just some static thing. Nope, it's this super dynamic mixture. You've got the solid part, which is all your minerals and organic stuff. Then you've got the liquid part, that's the water. And you've got the gas part, the air that's filling in all the little gaps. All three are working together in this constant, well, dance.
Okay, to really get what makes soil tick, we have to zoom in. I mean way in. We're talking about its most active, most powerful little components. This is where all the action really happens.
Say hello to the soil colloid. Now the name comes from a Greek word that means glue-like. And honestly, that is the perfect way to think about them. These tiny, microscopic particles of clay and decomposed organic matter, we call that humus, they are the chemical engine of the soil. This is where nutrients get stored, swapped, and exchanged.
But how in the world do these tiny particles get so much power? Well, the secret starts way down at the atomic level, with the basic architecture of clay itself.
For a second, just forget all the complicated chemistry. I want you to just imagine you're building with two different kinds of Lego bricks. One is a flat sheet built around silica atoms, and the other is a sheet built around aluminum atoms. That's it, just two pieces.
And the process is actually pretty straightforward. You start with those two sheets, the silica-based one, which we call tetrahedral, and the aluminum-based one, the octahedral. Now, if you stack them one on one, you get one type of clay. But if you make a sandwich with that aluminum sheet tucked between two silica sheets in a 2-to-1 ratio, you create a totally different kind of clay with completely different powers.
And that little difference in stacking, it's huge. It's a game changer. Over on the left, you see the 1-to-1 clays. They're stable, they don't really expand, and they can't hold on to many nutrients. But those 2-to-1 clays on the right, whoa, they act like an accordion. They literally swell up when they get wet and shrink when they dry, giving them this massive internal surface area. And that means they can hold on to a ton of nutrients. These are the powerhouse clays that make the world's great agricultural lands so incredibly fertile. Now, here is the secret ingredient. As these clay minerals are forming over millions and millions of years, tiny little imperfections happen. An atom gets swapped out for a different one. It's a similar size, but, and this is key, it has a lower positive charge. So for instance, a magnesium ion might just slip into a spot where an aluminum ion was supposed to be. And that one tiny atomic swap, it completely throws off the balance of the whole equation. You can think of it like a permanent little manufacturing defect that leaves the entire clay particle with a net negative charge. And believe me, that negative charge changes everything.
And this negative charge is the absolute key to one of soil's most vital jobs, building a storage system for life itself.
Because you know how opposites attract, right? Well, that negatively charged clay particle now acts just like a magnet. It grabs and holds on to all these positively charged nutrients that are just floating by in the soil water, things that plants absolutely need to survive, and it stops them from just getting washed away by the next rain. It's like a natural pantry. Now, scientists have a name for this nutrient storage ability. It's called the cation exchange capacity, or just CEC for short. You can really just think of it as a simple rating for fertility. A soil with a high CEC, like those 2-to-1 clays we just saw, it can hold a lot of nutrients. A low CEC, well, it means those nutrients are much more likely to just get lost.
So what kind of nutrients are we even talking about here? We're talking about essential building blocks for plants, things like calcium, magnesium, potassium. All of them are positive ions. We call them cations, and the soil holds on to them, keeping them ready for plant roots to come and grab them.
But look, this really clever chemical system, it's only half the story. Soil isn't just a pantry, it's a planet, a bustling, hidden metropolis absolutely teeming with an incredible amount of life. The scale of this life is just staggering. Get this, in a single gram of healthy soil, that's about the weight of a paperclip, there are over 1 billion bacterial cells. Let that sink in. That's more bacteria than there are humans on the entire planet, right in a little pinch of soil. And this vast community is working 24/7, recycling the very nutrients those clay particles are holding. You've got bacteria, the main decomposers.
You've got fungi using these powerful enzymes to tackle tougher stuff. You've got actinomycetes. They're the ones that give soil its classic earthy smell, and they even produce antibiotics we use in medicine. And then you have protozoa acting as predators, keeping the whole system in check. It's a complete, self-regulating ecosystem.
Okay, so we've gone from atomic structures all the way to microscopic life. Let's zoom all the way back out and connect these tiny details to the world that we actually see around us every single day.
And here's the bottom line. It's all connected. That tiny and visible atomic swap that gives clay a negative charge, that's what holds the nutrients in place. That hidden world of microbes, they're the ones that make those nutrients available for plants. And together, they determine whether a field can grow our food, whether a forest can thrive, and ultimately, they support pretty much all life on land.
So, understanding all this complexity, this really intricate dance of chemistry and biology that's happening right under our